puddling was one step in one of the most important processes of making the first appreciable volumes of high-grade bar iron during the Industrial Revolution. In the original puddling technique, molten iron in a reverberatory furnace was stirred with rods, which were consumed in the process. It was one of the first processes for making bar iron without charcoal in Europe, although much earlier coal-based processes had existed in China. Eventually, the furnace would be used to make small quantities of specialty steels. Though it was not the first process to produce bar iron without charcoal, puddling was by far the most successful, and replaced the earlier potting and stamping processes, as well as the much older charcoal finery and bloomery processes. This enabled a great expansion of iron production to take place in Great Britain, and shortly afterwards, in North America. That expansion constitutes the beginnings of the Industrial Revolution so far as the iron industry is concerned. Most 19th-century applications of wrought iron, including the Eiffel Tower, bridges, and the original framework of the Statue of Liberty, used puddled iron. Later the furnaces were also used to produce a good quality carbon steel. This was a highly skilled art, but both high-carbon and low-carbon steels were successfully produced on a small scale, particularly for the gateway technology of tool steel as well as high-quality swords, knives and other weapons. History: puddling was one of several processes developed in the second half of the 18th century in Great Britain for producing bar iron from pig iron without the use of charcoal. It gradually replaced the earlier charcoal-fueled process, conducted in a finery forge. It was invented by Henry Cort at Fontley in Hampshire in 1783 and patented in 1784. A superficially similar process was patented the previous year by Peter Onions. Cort's process consisted of stirring molten pig iron in a reverberatory furnace in an oxidizing atmosphere, thus decarburizing it. When the iron came to nature, that is, to a pasty consistency, it was gathered into a puddled ball, shingled, and rolled. This application of the rolling mill was also Cort's invention. 90 years after Cort's invention, an American labor newspaper recalled the advantages of his system. When iron is simply melted and run into any mold, its texture is granular, and it is so brittle as to be quite unreliable for any use requiring much tensile strength. The process of puddling consisted in stirring the molten iron run out in a puddle, and had the effect of so changing its anatomic arrangement as to render the process of rolling more efficacious. Cort's process only worked for white cast iron, not grey cast iron, which was the usual feedstock for forges of the period. This problem was resolved probably at Merthyr Tydfil by combining puddling with one element of a slightly earlier process. This involved another kind of hearth known as a refinery or running out fire. The pig iron was melted in this and run out into a trough. The slag separated, and floated on the molten iron, and was removed by lowering a dam at the end of the trough. The effect of this process was to diesel-iconize the metal, leaving a white brittle metal, known as finer's metal. This was the ideal material to charge to the puddling furnace. This version of the process was known as dry puddling and continued in use in some places as late as 1890. The alternative to refining grey iron was known as wet puddling, also known as boiling or pig boiling. This was invented by a puddler named Joseph Hall at Tipton. He began adding scrap iron to the charge. Later he tried adding iron scale. The result was spectacular in that the furnace boiled violently. This was a chemical reaction between the oxidized iron in the scale and the carbon dissolved in the pig iron. To his surprise, the resultant puddle ball produced good iron. One big problem with puddling was that almost 50% of the iron was drawn off with the slag because sand was used for the bed. Hall substituted roasted tap cinder for the bed, which cut this waste to 8%, declining to 5% by the end of the century. Hall subsequently became a partner in establishing the Bloomfield Iron Works at Tipton in 1830, the firm becoming Bradley, Barrows and Hall from 1834. This is the version of the process most commonly used in the mid to late 19th century. Wet puddling had the advantage that it was much more efficient than dry puddling. The best yield of iron achievable from dry puddling is a ton of iron from 1.3 tons of pig iron, but the yield from wet puddling was close to 100%. The production of mild steel in the puddling furnace was only achieved in about 1850 in Westphalia, Germany, and was patented in Great Britain on behalf of Lloyd, Brehm and Larkind. It worked only with pig iron made from certain kinds of ore. The cast iron had to be melted quickly and the slag to be rich in manganese. When the metal came to nature, it had to be removed quickly and shingled before further carburization occurred. The process was taken up at the Low Moor Iron Works at Bradford in Yorkshire in 1851 and in the Loire Valley in France in 1855. It was widely used. The puddling process began to be displaced with the introduction of the Bessemer process, which produced steel. This could be converted into wrought iron using the Aston process for a fraction of the cost and time. For comparison, an average size charge for a puddling furnace was €800 £900 while a Bessemer converter charge was 15 short tons. The puddling process could not be scaled up, being limited by the amount that the puddler could handle. It could only be expanded by building more furnaces. Process. The process begins by preparing the puddling furnace. This involves bringing the furnace to a low temperature and then fettling it. Fettling is the process of painting the grate and walls around it with iron oxides, typically hematite. This acts as a protective coating keeping the melted metal from burning through the furnace. Sometimes finely pounded cinders was used instead of hematite. In this case the furnace must be heated for €5 hours to melt the cinder and then cooled before charging. Either white cast iron or refined iron is then placed in half of the furnace, a process known as charging. For wet puddling, scrap iron and/or iron oxide is also charged. This mixture is then heated until the top melts, allowing for the oxides to begin mixing. This usually takes 30 minutes. This mixture is subjected to a strong current of air and stirred by long bars with hooks on one end, called puddling bars or rabbles, through doors in the furnace. This helps the oxygen from the oxides to react with impurities in the pig iron, notably silicon, manganese and to some degree sulfur and phosphorus, which form gases that escape with the exhaust of the furnace. More fuel is then added and the temperature raised. The iron completely melts and the carbon starts to burn off as well. When wet puddling, the formation of carbon dioxide due to reactions with the added iron oxide will cause bubbles to form that cause the mass to appear to boil. This process causes the slag to puff up on top, giving the rabble a visual indication of the progress of the combustion. As the carbon burns off, the melting temperature of the mixture rises from 1150 degrees Celsius to 1540 degrees Celsius, so the furnace has to be continually fed during this process. The melting point increases since the carbon atoms within the mixture act as a solute in solution which lowers the melting point of the iron mixture. Burning them off causes the melting point to increase towards that of pure iron, and since the temperature of the puddling furnace is less than that which wrought iron melts, decarburized iron in the mixture start to solidify around the puddling bars. Eventually the carbon is mostly burned off and the iron comes to nature, forming into a spherical spongy mass, indicating that the process is complete and the material can be removed. The hook on the end of the bar is then used to pull out the large puddle balls of the material, about 35 €40 kilograms each, and 30 €38 centimeters in diameter. Sometimes a large pair of tongs are used to remove the puddle balls. These puddle balls are then transported to the hammer or squeezer by dragging them along iron slopes built between the furnace and the shingling equipment or, more commonly, the puddle balls are loaded into iron wheelbarrows and transported to their destination. Shingling expels slag and welds shut internal cracks, while breaking off chunks of impurities. The iron is then reheated and rolled out into flat bars or round rods. For this, grooved rollers were used, the grooves being of successively decreasing size so that the bar was progressively reduced to the desired dimensions. Some of the iron oxide is from the scales that form in the later steps of shingling and rolling. The quality of this may be improved by faggoting. Working as a two-man crew, a puddler and helper could produce about 1,500 kilograms of iron in a 12-hour shift. The strenuous labor, heat and fumes caused puddlers to have a very short life expectancy, with most dying in their 30s. Puddling was never able to be automated because the puddler had to sense when the balls had come to nature. Puddling furnace. The puddling furnace is a metal-making technology used to create wrought iron or steel from the pig iron produced in a blast furnace. The furnace is constructed to pull the hot air over the iron without the fuel coming into direct contact with the iron, a system generally known as a reverberatory furnace or open hearth furnace. The major advantage of this system is keeping the impurities of the fuel separated from the charge. There were two major types of puddling furnaces used in the United States. The first is the single puddling furnace, which is based on the same design used in England and, thus, the most common. The second kind is the double puddling furnace, which was most often found on the east of the Allegheny Mountains. The general design of a single puddling furnace is as follows. The footprint of the furnace was 3.3 euro 3.6 meters long, 1.5 euro 2.1 m wide and 1.5 m tall. The outer walls were 23 centimeters thick and made of typical brick and then covered by cast iron plates. Wrought iron square bars, called crossbinders, are run through the roof of the furnace and bolted to the cast iron plates to keep the roof from collapsing. The chimney was 9 euro 12 m tall and 40 centimeters square. There would be a small work hole allowing access to the fire, and a work door allowing access to the hearth. The average work door was 55 centimeters wide by 68 centimeters tall, lined with fire bricks on the inside and with a small square work hole for tools. The hearth is where the iron is charged, melted and puddled. The hearth's shape is usually elliptical. 1.5 euro 1.8 meters in length and 1 euro 1.2 m wide. If the furnace is designed to puddle white iron, then the hearth depth is never more than 50 centimeters. If the furnace is designed to boil grey iron, then the average hearth depth is 50 euro 75 centimeters. Due to the great heat required to melt the charge, the grate had to be cooled, else it would melt with the charge. This was done by running a constant charge of cool air on it, or by throwing water on the bottom of the grate. The fireplace, where the fuel is burned, used a cast iron grate which varied in size depending on the fuel used. If bituminous coal is used, then an average grate size is 60 centimeters or 90 centimeters and is loaded with 25 euro 30 centimeters of coal. If anthracite coal is used, then the grate is 1.5 ma, 1.2 m and is loaded with 50 euro 75 centimeters of coal. A double puddling furnace is very similar to that of the single puddling furnace, with the major difference being there are two work doors allowing two puddlers to work the furnace at the same time. The biggest advantage of this setup is that it produces twice as much wrought iron. It's also more economical and fuel efficient as compared to a single furnace. See also: crucible steel, decarburization, double hammer, steel making. Footnotes. Further reading: W.K.V. Gale, Iron and Steel, 55 ff. W.K.V. Gale, The British Iron and Steel Industry, A Technical History, 62-66. R.A. Mott, Dry and Wet Puddling Trans. Newcomen Soc 49, 153-8. R.A. Mott, Henry Court, The Great Finer. K. Barraclough, Steel Making, 1850-1900, 27-35. Overman, Frederick. The Manufacture of Iron, in all its various branches. Philadelphia, H. C. Baird, pages 259 euro 302. http www.academia edu extra special best black country iron puddling and wrought iron manufacture in the 19th century. Paul Belford's paper on Noah Hengley and Sons.